sorry. Oh. So, this is a very interesting effect. And I think we've, spent many decades in the past generating different types of experimental platforms to investigate and demonstrate various interesting phenomena related to quantum interference. The most common one is this really fancy looking setup, or this type of setup that involves lasers and beamsplitters and optical components such as photon detectors and path delay, wave plates, whatever, right? So this is a really convenient and versatile platform because we can piece together this at room temperature on an optical table, and we can fairly quickly reach a regime where we can start to probe some of these interesting, very non-trivial quantum effects. So this is all great and fun, but there is a rather frustrating limitation in studying interference effects using optics, and this is this really boils down to the lack of nonlinear elements in optical photons, right? So flying photons, they are great. They travel through fibers. You can split them or change their directions using simple optical components. But the problem is that everything in the system is generally linear. In order to study some of these interesting effects, we actually need highly non-classical nonlinear states, such as single photon Fock states. And this is actually relatively hard to generate in standard optics implementations. So this is one of the, I would say, limitations that stops the optical platforms from implementing some of these more complicated interference studies. So this is where I think superconducting circuits could come in, because it's actually a much more engineerable system. Everything is essentially built with components that we can design and fabricate on demand, right? So this is generally described by the circuit quantum electrodynamics framework. So little c QED, which is sort of analogous to the cavity QED framework, where we actually describe the interaction between an optical cavity and a real atom, right? So in this case, we can have very precise models that tells us the way the interaction takes place, the various different loss mechanisms, and all these physical principles actually translate quite nicely in the circuit quantum electrodynamics framework, where we allow an electrical oscillator, usually in the microwave domain, to interact with an artificial atom, which is essentially constructed by putting together various different types of circuit elements. So this is really very, very similar to piecing together, conventional capacitors and inductors and resistors in our conventional circuits. So the key element here is that we need to engineer this nonlinearity, which is given by nature in atoms. But in the electrical circuits, in the quantum circuit framework, we have to engineer this. And this we could do by introducing a highly nonlinear element called the Josephson junction. So this is actually a really old piece of technology. It was developed in the 1960s by Brian Josephson. It's essentially just a sandwich of superconductors separated by an oxide tunnel barrier. Okay, so this is a picture of a simple Josephson junction, and you can see that this is actually relatively mesoscopic, right? It's hundreds of nanometers, and you can see these features with the 2 layers of superconductor and very thin, barely visible layer of oxide in between. Okay, so this is generally our playground for implementing various different types of experiments in circuit QED. So just to give a little bit more introduction about the components of circuit QED. The most basic one, as we were shown before, as it was shown before, is the LC oscillator. So this plays the role of the cavity, which usually can be made by 2 mirrors in the optical domain. So in the circuit regime, we just have essentially capacitors and inductors, and the way they behave is that they essentially reproduces the dynamics of a harmonic oscillator, where the position and momentum correspond to the charge and flux of the circuit, of the capacitor and the inductor, right? So with this, we can easily write down the Hamiltonian. Well, we start from the Lagrangian, we write down the Hamiltonian, We can figure out the resonance frequency associated with this particular type of LC oscillator. And we can figure out the spectrum, which is, at this point, harmonic, right? It's a quadratic potential with evenly spaced energy levels. So everything is degenerate, not super interesting. But the good thing is that, with this, the simple setup, we can actually manipulate it to be in a quantum regime where we can discretize each of the energy transitions. So the two requirement is that we need to first make the system in the regime where it is much, much lower. It's safely confined to its ground state, which means that we need to achieve very, very low temperature, right? So this can be done in commercially available cryogenic systems now, so it's no longer really a challenge. The other requirement is that we needed to store energy long enough for us to learn about the state or the distribution of the energies in the system. So this is done by designing it sufficiently well such that the dissipation or the noise present in the system is minimal compared to the coherence times of the oscillator. So traditionally or conventionally these days, you will hear things like, quantum circuits made out of aluminum, niobium, etc., a few standard superconductors, and everything will be cooled to millikelvin temperatures, where we safely satisfy the ground state regime using commercially available dilution refrigerators. So this is, a fairly trial and tested and tried setup these days. So if we just, recap on what I said about this simple system, right? It's great. It's very useful for us to consider the quantum regime of things for electrical circuits, but it's not super interesting because it's all the energy levels of the oscillator are degenerate. So we can't really do any non-trivial manipulations on it. To circumvent that problem, we have to introduce some sort of non-linearity. Okay, but before we talk about the non-linearity, I just want to, put this, LC circuits in a little bit more concrete form. It can actually be physically realized in a variety of different ways. So generally, we classify them under three architectures. One is the planar or the 2D, so everything is on the same plane, basically metal strips on a certain chosen substrate. And the other type is the 3D design, which essentially is a box that provides, good confinement, good trapping of the stationary fields of microwave frequencies. So here is actually one of the currently very popular designs. Is really just a cylindrical structure machined out of high purity aluminum, and its mode structures are basically defined by the dimensions of these features. Okay, so conceptually, these are pretty easy to understand. The relatively new development is called this 2.5D architecture, which is really interesting if you think about it, because it actually combines, this kind of 3D geometry where a lot of the electric field is stored in vacuum, which is very coherent, with the small, compact form factor of the planar structure. So by extending the dimensions, one dimension, and really shrinking the other one, we can make this very small footprint structures that still has high coherence properties, right? And this can be done using a very old technology called micromachining, where we etch shapes into silicon wafers and bond it with another top wafer, where we can put in like communication lines and vias to couple to the system. Okay, so I guess these three are currently the three main ways of realizing a superconducting cavity or a superconducting LC oscillator. Okay, so now let's move on to talk about the nonlinearity that is crucial for making the junctions, for making the oscillators actually useful. And this comes from Josephson junctions.
Excuse me. Yes. Can I interrupt?
Yes.
Okay, so I have a silly question regarding the, like how I can see that the phi and q, they are like conjugate variable, because you take them as like two conjugate variable of the, could you elaborate a little bit?
Yes, so this is actually a really good point, and it's a little bit subtle. So I guess I can give an intuitive picture for this.
Yeah,
You can think about, in the quantum regime, the charge accumulation on the capacitors on each of the capacitor plates, right? It could be either on one side or the other. So in some sense, the difference of the charge matters, but it doesn't matter which way the charges are arranged. Right. So in this sense, you can think about it as being in a superposition of being all accumulated on the one plate or the other. So in a very similar way, the inductor, right, you can think about the current flowing through the inductor. So you could flow one way or the other, but essentially it would give the same flux, right, with a different sign. So so that's how I can how we can think about the quantumness of an inductor, the flux variable and the charge variable. Does that kind of make sense?
A little bit. Maybe I'll think a little bit more.
Right. So if you like to get to the bottom of it, I think writing down a few lines of the math really helps, because it starts with a standard Lagrangian Hamiltonian, and then we pick out the then we can spot the commutation relations and choose the conjugate variables. So it's a very standard formalism for quantizing.
Yeah, because one thing that I don't understand, that when you fix where the charge is, the negative charge, let's say, then you already fix the direction of the current. So then the direction of the flux is already fixed by that, or
so.
Right?
Well, so the flux through the junction, for the flux through the inductor, you can think about it as
the polarity of the current.
Yes, but you're saying the polarity of the current is correlated with the way we fix where the charges are accumulated, correct?
Yes, because they're like to some extent parallel to each other. But they have a common ground, I think, already.
Yes, they do. So so I think, in this case, maybe it's not super clear about the math, but in general, I think it's the difference of the charges on each plate, and then the sort of differential current between the two nodes of the inductor.
I see. Okay, thank you.
Yeah. Okay.
Yes.
Great.
Thanks.
I think there's a tiny bit of feedback from somewhere. Okay, that's good. Perfect. So I'll move on to talk about the nonlinear element, which is, going back to the Josephson junctions. Again, this looks very similar to what we talked about in the LC oscillator case, right? We have a capacitor, but instead of a linear regular inductor, we now have a nonlinear inductor. So a junction is usually represented in the literature as a box with a cross. And what it is just this kind of tunnel junction with two layers of superconductor and a thin outside layer in between. And this is a very standard sort of side view profile of this, just to give you a little bit of intuition about what it looks like once you cut it in the cross section. But generally, you can see that this is actually a pretty easy structure to fabricate. And by controlling the size of the junction or the thickness of the barrier, we can actually very, very precisely engineer the characteristics of the junction, right? And therefore the characteristics of the devices we build with this junction. So this is a fully engineered system. And again, I guess just to highlight that everything is superconducting, so the tunneling across the the oxide barrier is actually done in a way that's without dissipation by this little Fred egg looking thing, which is a Cooper pair, right? So they always tunnel in pairs, hence doesn't cause any dissipation during the process. So the formalism developed by Josephson is essentially captured in the Josephson relations. What it says is that the critical current will depend on the flux across the junction in a way that's either a sine or a cosine, depending on how it's defined. And as a result, we can define an energy associated with the junction, as well as the Hamiltonian related to the junction. So without going too much into the math of this, I will just show that this is the general Hamiltonian of a circuit element that looks like this, where we'll have the charge degree of freedom represented by the charge of the capacitive, the capacitive energy times the charge degree of freedom, and then the nonlinear inductor is captured by the inductive energy times the cosine of the phase across the junction. Okay, so you can see that all of these parameters are essentially customizable or can be engineered on demand to fit the particular type of system parameter that we wish to achieve. Okay, so this is really a big advantage in terms of developing tailored platforms to study certain effects that we're interested in. Okay, so now we have the two main elements of a quantum circuit. The next thing we should do is to think about how they can interact with each other, right? So these are the two things we've introduced earlier. The most standard way of putting them together is simply to introduce a capacitive coupling, right? So in a circuit that will look like this, where you have the linear mode and a nonlinear mode with a capacitor that couples them. And the Hamiltonian of this actually looks quite intuitive, right? We have the linear mode given by the ladder operators times the transition frequency. And the nonlinear mode, if we assume that it's simply two levels, then it's essentially has a well-defined transition frequency associated with going to the excited state. And then there's a final term, which is really crucial for all the future operations that we'll introduce. It's called the dispersive coupling, which is essentially a state-dependent frequency shift between the two elements, right? Between the linear and the nonlinear modes. So physically, what this means is that if we have excitations in the cavity, it shifts the frequency of the artificial atom and vice versa, right? So this is a symmetric term. So in the frequency spectrum, we can see that on the one side we can use the transmon state to differentiate we can use the cavity frequency to differentiate the transmon state, and on the other side, if we use the reciprocal picture, then we can use the transmon to tell us how many photons are there in the cavity, right? So this is a very useful tool because from here we can already see that now we can actually have a way to selectively address certain photon numbers in the cavity. Okay, and we can also use this shift in the cavity frequency to quickly read out the state of the transmon. Okay? So there are a few different functionalities, all building from this type of simple dispersive interactions. Okay, so with this, that's essentially all the core components that we will need to run the interesting circuit experiment. Okay, and just to be a little bit more concrete, a system that will be useful for studying interference looks something like this, where we can have two cavities. So this is the top view, and these two are those cylindrical 3D structures that I've shown earlier. They have their own frequencies and usually detuned from each other. I can introduce a nonlinear element that capacitively couple to each of them, right? So there are no direct couplings between Alice and Bob, but the only way they can couple to each other is mediated by this nonlinear mode in between, okay? So physically, it looks something like this. You can see this is not a tiny structure. It's actually, you can hold it with your hand and actually look at it. So, this is a very common architecture these days in the circuit community to study, bosonic structures and, error correction implementations. So with this structure, we generally could identify or we can label a few different modes, right? So for these 3D cavities, we make them extremely long-lived, so they're very weakly coupled to the transmission lines and the environment. So their lifetimes are on the order of milliseconds. And then we can engineer these nonlinear modes to be roughly 100 microseconds. Apologies, this is supposed to be microseconds. We wish there's millisecond coherence, but not yet. And then we can actually introduce another kind of linear mode, which is just a sort of a lambda over 4 resonator, and couple it very, very strongly to the environment to be the readout mode that's very short-lived. So just by carefully tweaking the coupling to the environment and sort of design the geometry of each parts, we can actually achieve several orders of magnitude in separation of their coherence time just in the same architecture. Right, so the reason why we do this is because for studying interference, we want photons to be present for a long time. So we put it in this long-lived mode. And then we want to use these nonlinear modes as ancillas to control the linear mode. So we want to have quick and effective gates on these, so they're a little bit more strongly coupled to the environment. And finally, we want to extract the quantum state in our system very effectively and very quickly. So we make a very short-lived and strongly coupled mode to give us that signal once it's ready to be extracted from the system. Okay, so these are all sort of engineered for the specific, for the role of each mode to have this kind of system parameters. Okay, so with this architecture, we can now think about how to study, how to test out some quantum interference effects. The one thing we need to note is that if I just have this and have the natural interactions, which is dispersive, then the photons we put in Alice will not talk to the photons we put in Bob, right? Because they're detuned, and we all know that if you have two beams of this different frequencies, they naturally do not talk to each other or interact with each other in any way. So if we really want to see how we can implement some sort of interferometry between the two, we have to come up with a way to convert their frequencies from one to another. And this can be done using some techniques in the sort of quantum amplifiers works several years ago. And it's essentially also borrowing from nonlinear optics, I guess, is to use our nonlinear element as a frequency converter. Okay, so this is very similar to using a strong laser beam to pump a nonlinear crystal so that you can have frequency conversion between the different modes depending on the pump frequency. Okay, so this is essentially the same philosophy, except that the drives are now a microwave, and then a nonlinear medium is a Josephson junction instead of a nonlinear crystal. So with this in mind, we can choose the drive frequency such that it could give us a certain interaction term or a certain type of conversion between the frequencies. So the choice that we made is that we put in two drives, omega 1 and 2, such that the difference in their frequency exactly matches the difference in the resonance frequencies of Alice and Bob, right? So this actually provides the energy conservation that's needed to convert one excitation from Alice into one excitation in Bob and vice versa. Okay, so with this kind of drive, the resulting Hamiltonian will look something like this, where we have a certain time-dependent coefficient that either takes a photon from Bob and put in Alice, or the other way around, right? So what this means is that now, if we just do a simple test of putting one excitation in Alice, and then we turn on this interaction, we should see that it should just go coherently back and forth between the two cavities. And we can probe this pretty precisely by measuring the probability of P 1 in Alice, 0 in Bob as a function of the evolution time. And you can see that it coherently oscillates from a high amplitude to almost to 0 and just back and forth for over 100 microseconds, okay? If we do the opposite measurement of, asking the question, basically, when do I have, what's the probability of having no photon in Alice but one photon in Bob, then we get the we get the same oscillation exactly out of phase, right? This is what we would generally expect if we have indeed engineered this particular interaction between the two cavities. So one thing to note is that here, this is raw data, not average, not corrected for any sort of detection efficiency and things like that. You can see that at most it goes to about 0.8 in the probability instead of 1. And this is precisely due to this uncorrected detection efficiency, which is really a sort of reduction in contrast without much distortion. And the way we can tell that it doesn't add distortion or doesn't add bias is because you can see that the oscillations, if you sum them up, they actually have a fairly exponential looking envelope that essentially tells us the, on average, how quickly does a photon gets lost in the system, right? Because eventually you will have to decay to 0 where the photon is irreversibly lost from both of the cavities. So this amplitude here is simply an indication that our detector, which is our readout in the system and the mapping of the parity of the photon number to the ancilla, is not as efficient. So it's not a fundamental limitation, just in this particular measurement that it wasn't as effective as it could have been. Okay, but this actually, this kind of simple probe actually gives us quite a lot of insight on the system. And it tells us that if we pick the right evolution time, we can engineer a gate that's a full swap between the two cavities. So you take all the excitations from Alice, you put it all in Bob, or the other way around, right? And if we choose half of that evolution time, we essentially achieve a 50-50 beam splitter. Okay, and this is actually really useful because we want to study interference, and generally we need beam splitters to study interference effects. Okay, so building upon this, we can do a little bit further, right? The first test we did is simply on a single photon Fock state oscillating back and forth between the two cavities. To make things more interesting, or to probe whether the effect actually preserves, prepare a slightly more interesting state where Alice is in vacuum, but Bob now is in a superposition state of 0 and 2. So if we prepare this state and put it into two beam splitters, we actually get a full transfer of this non-trivial quantum state into Alice, and keep and completely remove all the excitations from Bob. Okay, so this indicates that our operation actually respects the phase coherence as required by keeping the quantum coherence in the interference studies we want to build later. Okay, good. So I think this is sort of the simplest test we could do when we have something like a swap gate or a beam splitter operation, right? To make it a little bit more complex, what we want to do is to see the photon statistics when we actually interfere them through this beam splitter. And yep.
So I have two questions. One
yes.
is that what determines the sign of the interaction, the nonlinear interaction?
Sorry, what is the sign of the
what determines the sign of the nonlinear interaction, the chi?
So the chi is always negative. And this
I
is
see that you put an attractive interaction, negative chi in the Hamiltonian. So why the energy will always reduce when they interact?
Sorry, you mean like a few slides back?
Yes.
Yes, okay. So the sign of the chi is somewhat related to the, so I always think about it in, you expand the cosine, and you can pick out the second order term, fourth order term, and etc. And basically we have, if you remember the, it's basically the capacitive energy minus the inductive energy, right? So the fourth order term is positive in the cosine, and once you minus that, it becomes negative. So it's not the most intuitive thing. But let me try to be in the physical sense, right? The nonlinear mode, consisting of the junction and the capacitor, for example, it has a nonlinearity which is positive. What that means is that the transition energy between the 0 and 1 state and the 1 to 2 state has a difference. Reverse. The 0 and 1 state has a larger transition frequency compared to the 1 and 2 state. So all the peaks are shifting closer to each other. So nonlinearity takes your it's in the direction it's a. They
squeeze the the spectrum to the lower side.
Yes, exactly. So this sign actually, when you do the math, it actually translates it. It becomes consistent with the chi as well. So sorry, I don't think I have a much more intuitive way to say this, but I think a couple lines of math would make it clear if we have a board.
Thank you. I think it's better now. And I have another question that when you couple two harmonic oscillators, then you see a complete exchange of the particle from one to another. So this is like a linear interaction between a double well potential. So, and what do you see? Just one frequency. So, and is the interaction term still linear or non-linear?
So this interaction Hamiltonian is bilinear.
It's bilinear, right?
Yes. So
there is no non-linearity yet. That's
no,
why
not
you
yet.
see one frequency in your Rabi frequency, one Rabi frequency only.
Exactly. And actually, that's a really good point, because the next thing I want to show is the Hong-Ou-Mandel interference, right? And we know that this actually shows some weird quantum nonlinear behavior, but it's because we're putting in highly nonlinear states in the input of our bilinear beam splitter, rather than, you know, generating nonlinearity through the beam splitter itself. Does that make sense?
Yeah, thank you.
Okay, cool. Thanks for the question. So I guess, you know, it's a little bit of a spoiler on the slide, but essentially what we want to do is to observe this kind of interesting statistics when we put in two photons from on each port of this beam splitter, right? So what we expect to see is that it should come out either both in one or both in the other randomly, and on average about equal probability. And what we measure is essentially, you know, directly in agreement with the expectation. So this is a plot of the frequency as a function of evolution time, and the z-axis, so the color, is the probability, right? So along this line, we have the probability of both photons in Bob, and this line we have probabilities both in Alice, and in the middle is one in each, right? So you can see if we start from 1, 1, then we start with a high probability of one photon in each cavity with no probability in these two photon states. But as we evolve for a certain period of time, we get to a equal superposition, roughly equal superposition of the 0, 2, and 2, 0, with pretty much no possibility left in the 1, 1 combination. Okay, so what this actually tells us, so sort of the peak and the trough here gives us a really good indication of how good our beam splitters are in making our two previously fully distinguishable photons, because they have different frequencies, now indistinguishable, such that they can undergo this kind of Hong-Ou-Mandel interference, right? So the fact that we can achieve this tells us our beam splitter is actually doing a really good job in making them indistinguishable. But what's more interesting is that because we have, you know, non-flying photons, we have photons trapped in the cavities, we can actually go through many cycles of this, right? So we can let it evolve some more, and we actually refocus back to 1, 1 almost fully, and no longer stay in a 0, 2, 2, 0 possibility, right? So we can just let this evolve continuously, and it will just oscillate back and forth between these two possible combinations of states. And the fact that you could fully refocus is another indication that the phase between the 0, 2, and 2, 0 combinations are extremely well preserved, because otherwise it will be incoherently adding up, and will not see this full refocusing of the 1, 1 combination. Yeah. Okay, so this is, you know, the effect is not new, but I think using quantum circuits or superconducting circuits to probe this effect actually adds a little bit more flavor, in the sense that we can now actually capture the whole evolution of the behavior of the interference behavior, rather than just having one instance of and collecting statistics, right? Okay, so the next thing we could do is, you know, continue, you know, make use of this interesting, or this new functionality of being able to monitor the full evolution to make more complex looking interferometry. So one way to do that is to simply think about Mach-Zehnder interferometers, but cascaded together, right? So again, the setup is very similar. We put one photon in each port of the beam splitter, so each cavity, and then we can re-interfere them and measure what's the outcome. And along the way, we can actually also add a phase to one of the cavities if we wish to, right? So we have these knobs, and this phase can be introduced simply by using the nonlinear ancilla that couples the cavity and using the natural dispersive interaction. So if we actually start like this, we can see that in the same way of measuring, we see that we start with the 1, 1 combination, and then we go to the 0, 2 plus 2, 0 combination, right? After one beam splitter. But then if we put a phase of pi here, we actually change the relative sign between the 0, 2 and 2, 0. And the following set of beam splitters will actually change the destructive and constructive interferences that's occurring in the system, right? So in order to go back to 1-1, we actually have to allow the 1-1 probabilities to constructively interfere, while the others destructively interfere away. But by putting a phase, we can actually prevent that from happening. So we only have the possibility of staying in 0-2 and 2-0, while all the probability amplitudes of 1-1 destructively interfere, right? So we can keep it in this kind of dark state or engineered dark state for as long as we want, if we just continue on with the evolution. But we can fully reverse this by simply putting another phase at a later time. And when we do this, we can, if we choose pi again, then we can just resume the normal Hong-Ou-Mandel type of interference, and then you can just continue on as you would, right? So you can see that we have very good control of exactly the kind of interference we want to engineer, and everything is on demand, right? So adding a phase is simply introducing, is using a microwave drive. So we do not have to move any beam splitters or any phase plates, for example. We can introduce this on the fly as part of the experiment, so everything can be engineered to switch the dynamics of the interference on while in real time while the experiment is happening. So this is, again, a really interesting demonstration of the additional functionalities that quantum circuits could bring into the study of quantum interference. Okay, there's a little bit of additional residue that you can see that's showing up in other combinations, and this is because in this particular measurement we were suffering a little bit from the photon loss in the cavities, so that eventually we're starting to see the cases where both photons have left the cavity, and we're starting to pick up the probabilities there. Okay. But overall, I think this is a very interesting way to look at interfering different frequencies, sort of photons of different frequencies. We can push this even further and maybe think about things like boson sampling, right? Because in these cavities, we can initialize more than one photon. We can initialize a cat state or a 5-photon stage or a coherent state, right? So if we make use of that and say, what if we put in a different kind of combination, where it goes through this, this kind of interferometer, and what kind of distribution are we going to get at the end? And this is, a bit of like the classic games of Pachinko and stuff like that. So we did that in a very, crude demonstration. We just put in 2-1, so 2 photons in one port and 1 photon in the other. And we just monitor its evolution as a function of time again. And with this, we see that, if I do a 1D cut, plot it here, it's a bit easier to see. We see that the evolution or the statistics of the photon distributions very quickly gets quite complex, right? Even just with 3 excitations, we can already see that it's a lot harder to analytically predict where we get superpositions and where we get full refocusing and things like that. But with the quantum system, we can simply do this measurement and accumulate the results to give us that information. So it's pretty efficient. So this makes us, this could open up ways for doing more complicated boson sampling experiments using similar architectures, right? So this is a very, very crude first demonstration of that. Another really interesting effect that we could do, again, using all the basic tools we've developed here, is to have a very efficient meter of the overlap between 2 quantum states. So this draws inspiration from the AMO community, where when you compare the states of different numbers of atoms, they actually use a Beamsplitter and essentially compare the parity of the outcome and use that to say, are the 2 input states same or different? And again, this is purely based on the destructive and constructive interferences, right? So in this case, if we put in states like this, all the even states will constructively interfere at the end, and the odd ones will destructively interfere. So if we measure a parity at the outputs that's even, then we know that the input are the same. And if we measure odd, we know that they were different, right? It doesn't reveal the information about the states themselves, but it only extracts the bit of information that tells us whether they're the same or not. So in some sense, it's a little bit like a classical probe of the difference between 2 quantum states. So this conceptually is quite straightforward. In implementation, we actually have all the knobs already, right? We have the Beamsplitter. We also have the nonlinear ancilla with the dispersive shift that could do parity mapping or phase mapping. So what we do is that we initialize 2 coherent states in this case. And this is really for the simplicity of the illustration. If we put them into the Beamsplitter, and then we do a parity map, which is essentially saying that now I want to map the parity of one of the cavities onto a state of the nonlinear ancilla. And this is done purely using the natural dispersive interaction. If we do that, what we observe is that as we sweep the phase of the other guy, we see that it peaks when they have the same phase, and it becomes 0 when they're exactly out of phase. So when they're maximally different from each other. Okay, and then when we repeat this for the different size of coherent states, we see that it gets narrower, the overlap, which makes sense because the larger the coherent state, the more sensitive to the slight differences in the angle where they are, the phase of the coherent state. Right, so this is actually a really effective way to ask the question of, are my 2 states the same? Okay. Finally, I think what we wanted to do is to say, can we now use this bilinear term and add a little bit more operations to make it an entangling or a non-linear operation? So the reason behind this is a lot of the quantum information processing tasks requires at least 1 entangling operations. So if we want to use the cavities, for example, as our information carrier, then we need to figure out a way to entangle them. The Beamsplitter itself, like we were talking previously, is bilinear, so it doesn't provide entanglement, right? If we put in a semi-classical state, for example, then the outcome is purely classical and fully separable. There is no entanglement there. So in order to generate entanglement using our Beamsplitter, we can, think a little bit more out of the box, or go back to the intuition or the first principles, where the entanglement can be always generated if we can do a coherent superposition of a swap operation and an identity operation. So it's like if we swap and not swap at the same time, then we can entangle the 2 modes that's involved. So this is actually a really useful way to think about this, because there is a gate that essentially realizes this. And this is proposed by Planio and Lau in 2016. It's called the exponential swap unitary operation. It actually has an additional function that is fully tunable by the angle on an ancilla. So what it does is essentially saying, I can do a superposition of the identity and a swap operation parameterized with their weights parameterized by the rotation on the external ancilla mode. So this gate is actually really useful for information processing. So it's good for all the bosonic quantum error correction codes. It actually provides a full universal gate set for us to do any kind of computation we need. And it has other interesting applications like quantum machine learning, et cetera, et cetera. Right? So this is a great unitary, and we went ahead to try to implement this. In the interest of time, I won't talk too much in details of this, and I'll be happy to discuss afterward. But essentially what we could do is that we build upon our Beamsplitter and add some ancillary rotations such that overall we can achieve this E-swap gate. And the way we quantify that, just really as a show and tell, is that we can tune the theta, which is the control angle, to perform either the identity or the swap or the exact equal superposition of the 2. So what I'm showing here is the process tomography of the gate that we engineered compared to the ideal gates that we would have achieved if everything is perfect. So you can see that we're doing okay. It's not perfect. It's not super high fidelity yet, but generally we're getting to the high 80s and low 90s range. So it's a conclusive demonstration that we can indeed engineer such a unitary operation. Okay, so just to wrap up, I think in this talk, I've tried to squeeze in a lot of materials, and to summarize them is basically we can show that with this kind of 2-cavity mediated by a nonlinear mode architecture, we can implement interference experiments to achieve coherent state transfer between the 2 modes. We can have high contrast Hong-Ou-Mandel interference. We can also engineer on demand or program on demand different interference dynamics in the cascaded Mach-Zehnder interferometer. And finally, this also provides an interesting knob or interesting way to measure the similarity or differences between the two cavities using a very simple mapping of the parity. So all of these operations and effects that were studied are using this kind of bilinear operation that we engineered. And the reason why it's so useful is that it's deterministic, so we don't need to do post-selection or heralding. It's also state independent, so that we can put in any sort of initial state. For boson sampling, we can put in any sort of initial state and still use the same interaction to achieve the desired dynamics. And finally, this is useful also for quantum information processing because it's compatible with certain schemes of quantum error correction. Okay, so that's great. But I think what's more exciting is what's yet to come, right? This is a really useful tool, and this architecture can be extended into multi-modes with the same principles that we can adapt. So one thing that we've already done is to push this to be a useful module for quantum information processing using bosonic systems to build the exponential swap gate and the Fredkin gate. But there could be other things. For example, a larger scale boson sampling system where we can put in arbitrary input states and programmable Beamsplitters to study, the particular type of effects that we want to look at. We can also use this to do quantum simulations. There are actually 2 studies on this already. One recently came out from Yale using exactly the same hardware where they can simulate the vibronic vibronic spectrum of a molecule using this system and this type of engineered couplings, right? And I think it's also really exciting that, it's also really exciting that there's a lot of unknown in this. And I think this is where it'll be really good if you have, ideas you want to try out or things you want to discuss that could use architectures and operations like this to probe interesting effects in physics or chemistry or complexity theory or whatnot, right? So that's everything. Thank you for your attention. And if you're interested in working on these or talking to me about these, you can reach me at my US email. We also have a lot of details about our work as well as the positions available on our website. So yeah, thank you.
Thank you very much. Thank you very much, Yvonne. Very nice talk. So I think now the session is open for questions.
I have one.
Yep.
Okay, Christian, please go ahead.
Yes, I mean a very simple one. Okay. Okay, you are just starting at CQT, right? Okay.
Yes.
So suppose right now you have all the lab room available to you.
Mm-hmm.
How long does it take to have, a fully operational experiment? I mean, for what you want to do. Okay.
Yeah. Good question. I think optimistically, in a year's time, by this time next year, we want to have a operational experiment on a small scale, maybe a few modes only. But yeah, that would be, I think, optimistic, but also quite a reasonable time frame, barring any sort of global pandemics stopping us and unforeseeable circumstances.
Okay, and second question. Okay, among all the people who work on this type of systems. Okay, yep. Do you think you have everything that you need in the environment to be at the same level, or what would you need?
Yeah, I think yes. I think we're pretty blessed that in Singapore we have a lot of good, RF engineering, fabrication, quantum information theory. So in that sense, I think there's a lot of resources for me to leverage on and existing expertise. We are a little bit shy in terms of specific knowledge in quantum circuits. So I think for me, what I'm maybe currently lacking a little bit that I need to spend time to get to achieve is to build up a team, a core team that, that has the hands-on knowledge and the intuition about quantum circuits specifically. So I guess it's the team building that I'm focusing on a lot right now. And once we're operational, I think we'll be able to start to leverage on all these amazing existing capabilities in USNTU, SUTD, and the industries to develop new things to work on together.
And do you think also about, lectures for students, maybe second year, PhD first year, I don't know, whatever. Do you think it's would be good or not? I don't have any idea if this type of topics, specific topics are taught in Singapore.
Yeah, that's a good question. So I've actually given guest lectures in several classes over the past 2 years since I came back. But they're relatively, one-off things in a larger set of lectures. So yeah, I don't know. I think it's an open question. I don't know. A course specifically on this would be too narrow for students, at the 4th year or the early PhD level. But potentially, I think there are already courses on quantum devices in the US. So I think that could be a really, we'll probably try to incorporate more of the circuit elements in there as well, because it does fall under the same theme of quantum devices.
Okay. Thank you, Yvonne.
Thank you.
Thank you, Christian. So other questions? So yes, Mehdi, yes, please.
Okay. This is like when you introduce the phase phi to control the whether it will be 0-2 or 2-0.
Yeah.
Yeah. The microwave phase, does it if you control this particular phase, does it depend on when you start the microwave, the phase of the microwave? It starts from 0 or the maxima or some point, because it's in which superposition state you are.
Yes.
I'm not sure.
Yes, I think I roughly understand what you mean. So the microwave phase, it's important, but it's not the absolute phase. There's no way to count the absolute phase of the microwave drive. So what we do in, for example, in this case, is that when we want to put in the phase here, right, we just need to make sure that this, when we put in the phase here, is different by pi from the previous one. So it's always relative, not like an absolute phase we hard code into the microwave drive. Does that make sense?
Yes.
Yeah. So however we drive the no phase case, we just make sure the next drive, when we want to add a phase, it has a relative different phase difference.
Shift the polarity.
Exactly. We change the signs to cosines, for example. Yeah.
Okay, thanks.
Even in terms of technology for doing that, do you, so you are mentioning aluminum, superconductor and others at the beginning of your talk. So, is there any hope to that new material emerge, and maybe at higher temperature or something like that?
Yes, actually, I'm pretty sure this is being studied in a lot of places. I think there were some recent developments in using things like niobium, titanium, other types of superconductors to study this. But they're generally, they're higher temperature, but not not very high either. So you still need a cryostat and things to cool it down. I don't know if you could do this at room temperature, because there's just so much thermal noise from the signals alone. Yeah, I guess it's definitely possible to move it up to, say, 4K or 10K, where we can cool with liquid nitrogen. Like 100K, where we can cool with liquid nitrogen. But yeah, I'm not sure where we are in terms of room temperature superconductivity at this point.
Yes, I think what was more, you talk about dilution free.
Yes.
So you were more in the millikelvin range.
Yes.
Being already in the 4 Kelvin range can be a substantial improvement.
That's true. 4 Kelvin, yeah, there's actually a lot of very exciting developments in terms of the low temperature stuff at 4 Kelvin. So one of the considerations is that we want to move a lot of the control electronics into 4 Kelvin as well. So we can do everything much faster rather than, you know, having like 6 feet of cable going from the device to the room temperature and back down. So like the control signals doesn't have to go through all these potential dispersion and time delay before it gets to the device.
And in your talk, you didn't mention squeezing. So squeezing is really something
yes.
which is in quantum optics is very important.
Yes.
I mean, can you? I guess you can do that. You have all the necessary tools.
Yes, we can actually squeeze really hard. So yes, it's fairly straightforward to get, you know, comfortable, you know, good squeezing. Maybe not to get the state of the art is a little bit challenging, but for example, in this recent paper in PRX where they did the quantum simulation, squeezing is one of the components that they needed, and I think they were able to get to maybe like 10 dB, 6 dB, 10 dB, just fairly quickly with a little bit of tuning.
Okay. Yeah. Okay, so other questions?
I have a quick one, I guess.
Yeah.
Yes, Mali.
Hi, Yvonne. Very nice talk. Just, I guess, in line with the continuous variable stuff, I understand that when most people look at superconducting qubits, they're looking at discrete variable quantum computation. But could you comment on whether there's some interest in sort of looking at continuous variable information processing as well?
Yeah.
With generating CV cluster states, and especially now that the nonlinear operations, the things that are really hard in CV, right, that prevents it from going outside the Clifford group, you can actually do really easily with superconducting qubits.
Yes, absolutely. So, you know, well, I didn't have time to talk about the details of this. So that's really the motivation behind doing this untangling gate, because we want to use this kind of cavity states as the information carrier, as our encoded qubit. And so we definitely need to be able to operate, you know, do 2 qubit gates on them. So the reason why these CV variables encoded in cavities are appealing for us is because it actually provides a large Hilbert space in one piece of hardware, right? So we can actually do redundant encoding just by using the many different levels of the oscillator. So that way we gain in the Hilbert space, but we don't introduce any additional penalty of decoherence, crosstalk, and things like that. Yeah, so there's actually a whole range of research called bosonic quantum error correction codes that uses this philosophy.
Very cool. Now we use these. We look at the partial swap gates quite a bit in a few protocols as well. So there's a lot of interesting algorithms to do with these things, especially in continuous variable Hilbert space.
Yes. So for example, this one, we didn't know. We actually were just giving a talk somewhere, and someone was, you know, Adam's community just came to me and said, oh, you know, we do this all the time in atoms. I forgot what it is, neutral atoms. And then, you know, we was like, oh, but we can do that too. So we tried it. It works really well. So there's a lot of crossover once we start to build up the repertoire of the essential critical tools.
Great. Thanks. I'm looking forward to it.
Yeah. Also, if anybody has, you know, crazy new ideas using some of these tools and elements, I'll be very happy to talk about them.
Brilliant. Thanks. That's my question.
Okay, thanks. Thank you, Mile. Other questions? Okay, so I think if there is no other questions, so thank you again.
Thank you.
Thanks, Yvonne.
Yvonne, thank you so much.
Thank you, everyone.
Have a nice weekend and see you around.
Bye-bye.
Bye-bye.